I am going to show how to derive the hydrostatic differential equation. The hydrostatic differential equation is listed right here. The derivative of pressure with respect to elevation is the negative of the specific weight. The hydrostatic differential equation is important because everything in hydrostatics is derived starting with this very simple equation. This derivation has a PDF handout. To access this derivation, go to efm.wikidot.com. Go to the Lessons tab and open it. Go to the lesson on hydrostatics and open it. Scroll down to Requirement 3B and click on Handout. Situation. Define a fluid particle. Let this lie at an angle alpha with respect to the horizontal. The face area of the particle is delta A. The length of the particle is delta L, where we're using a lowercase l. Let the L coordinate axis be aligned with the particle. Whoops. And let's let the Z coordinate axis go up and down with respect to gravity. If we draw a little triangle, this will turn out to be useful in the derivation. This distance is delta Z, change in elevation. This distance is delta L, the length of the particle. This angle is alpha. We can write sine alpha equals delta Z over delta L. To apply force equilibrium, let's sketch a free body diagram. So here's the fluid particle. It has a weight downward. There's a pressure force pushing on this face. That will have magnitude of pressure, force per area, times the area of that face. Similarly, there's a pressure force on this face. That's the pressure plus the change in pressure going from this face to this face times delta A. You want to make this positive so signs work out correctly in the derivation. And now we can sum forces in the L direction. And so we have P delta A, this term, minus this term, minus P plus delta P, delta A, minus the weight term. And we have to pick up the component of the weight in the L direction. So that angle again is alpha. So that becomes minus the weight times the sine of alpha. That is all equal to 0. Specific weight gamma is defined as the ratio of weight to volume. The volume of the fluid particle is equal to the face area times its length, delta A, delta L. Therefore, we can say the weight of the fluid particle is specific weight gamma, delta A over delta L. Excellent. And we can come right in here and substitute. Similarly, we can substitute for sine alpha from the previous page. All right, here's our two substitutions, substituting for weight, substituting for sine alpha, and then P delta A will cancel out this P delta A. So this term and this term cancels, and we're left with minus delta P delta A equals, minus gamma delta A delta L delta Z over delta L, and that's all equal to 0. And this is step 4, combining equations. And let's see, delta A cancels. This delta L cancels with that term. And we can rewrite the equation as minus delta P over delta Z minus gamma equals 0. Almost done. We can rewrite the previous equation. So we have minus gamma as delta P over delta Z. We can take the limit as delta Z goes to 0. This becomes the definition of the derivative. And therefore we can write that as the first derivative of pressure with respect to elevation, or more commonly dP dZ equals minus gamma. We are done with the derivation. This is the final result. This is the hydrostatic differential equation. Let's look at what this means. If we assume that the fluid has a constant specific weight, this says that the change in pressure with elevation is equal to a negative constant. So this is an equation of a straight line, and what this means physically is that pressure will increase linearly with depth in a fluid of constant specific weight. So if we draw a picture of a water reservoir, it turns out the pressure right here will be 0, and if we go down in depth, we'll have a larger pressure. Let's indicate that with a vertical line. If we go down twice as deep, we'll have twice the pressure. And so what we see is pressure will increase with depth, and the slope of this is minus gamma. Or similarly, if we go upward in elevation, the pressure will decrease with this slope as shown here. If we sketch a liquid and draw a fluid particle, let's just take it spherical. This particle will have a weight, and what keeps it from falling is that there's a net force due to pressure acting upward. So we can say there's a force of pressure, and in hydrostatic conditions this force of pressure is exactly balancing the weight, and this is why this fluid particle remains in place. The differential equation tells us the exact same thing. dP dZ here, this is the net force due to pressure divided by the weight of the fluid particle. That's the meaning of this term. Net force per pressure divided by, instead of weight, that should be the volume of the fluid particle. And this is the weight of the fluid particle divided by its volume. And we put the 0 over here on the left-hand side. So all the hydrostatic differential equation tells us is the net force due to pressure on a particle divided by the volume plus the weight of the fluid particle divided by volume equals 0. The pressure force and the weight forces exactly balance out to give us equilibrium. Very simple idea.